Okay, so now we're going to talk about estimating sums of alternating series. And see, here's the thing about alternating series. That picture I drew in the previous video, it actually is going to illustrate a lot of different important things about alternating series, including what we're going to talk about here, which is the alternating series estimation theorem. The main idea is that every alternating series that converges has a finite value, and we have a good bound on that finite value. And I'm going to draw that picture again because it's just such a good picture. It shows all the beautifulness of a alternating series, even if it's just the schematic. So remember, we start at 0. And what we're doing is we're representing each partial sum as a combination of left and right movements along the real axis. So here's S1 equals B1. Okay. Here's S2 equals B1 minus B2. Here's S3 equals B1 minus B2 plus B3. Here's S4 equals B1 minus B2 plus B3 minus B4. Here's S5 equals, you get the point, right? Okay, why is this picture so helpful? So each time that I'm drawing this dotted line up to the real number line, I'm representing where we are now on at that nth partial sum, okay? So here's the first partial sum, right? Here's the second partial sum. Here's the third partial sum. Here's the fourth partial sum. And here's the fifth partial sum. Okay, why am I going through all this? Again, we already saw this picture. Because it turns out for all positive values n that are integers, the limit of a convergent alternating series is always going to be wedged between two consecutive partial sums. So the actual limit of this, the actual sum of the series, right? So S equals what happens when we actually go and carry this out all the way out to infinity. We have it somewhere in between each consecutive partial sum. So either S sub n is less than or equal to S, less than or equal to S sub n plus 1, or S sub n plus 1 is less than or equal to S, less than or equal to S sub n. Okay, so every additional term bounds the remainder, R sub n, which is the difference between the actual value of the series and the nth partial sum. And that's because each time we move closer and closer, we're zeroing in further until the remainder can't be any larger than the next term in the series. So here's the theorem. If this alternating series converges, then the magnitude of the nth remainder, so the tail up to the nth value, is going to be less than or equal to the next term in the series. Okay, so to visualize that, the remainder that we would get for the tail of the series after stopping at one term has to be less than, or the magnitude of it has to be less than b sub 2. Because we're only going back by b sub 2. So the actual distance between that and the limit, the diagram is a little confusing, admittedly. But this solid, very thick red line represents where the actual limit of the series is. And so really what we're visualizing here is that this purple line, right, is a bound on how far away the orange line is from the thick red line. And similarly, right, if we keep moving further out into the series, the remainder after terminating the series at the second term can't be any larger than the third term, and so on. So every next term is guaranteeing that we're never further away from the real value of the series than that next term. And here's why that's so powerful. Application. We're going to approximate the sum of n equals 1 to infinity from negative 1 to the n all over 2n factorial, correct to 4 decimal places. Okay, you may be wondering, how are we going to do that? So the point is that the alternating series estimation theorem says that if we bound r sub n, the magnitude of it, to be less than 0.00001, and you know that we can just find the n plus 1th term of this series, find the first term b sub n plus 1 smaller than 0.00001, then our actual value of the series cannot be more than this much away from our approximate value. And because we want it accurate to 4 decimal places, this last digit doesn't matter, right? So we will have it up to that value. So here's how we can do it. We're just going to add a few values of the term until we get one that's smaller than what we want. So here we go. The series has the first few terms, negative 1 over 2 factorial, plus 1 over 4 factorial, minus 1 over 6 factorial, plus 1 over 8 factorial, minus 1 over 10 factorial, plus, and so on. I'm going to stop there. And maybe this is enough, maybe it's not. Okay? So, this equals, and this is approximate, but no, this is exactly equal to negative 0.5, that's the first term, plus 0.41667 minus 0.00139. So one thing that I want you to notice is by this theorem, what we're saying is that after this term, we are accurate to 2 places after the decimal point, which is pretty powerful, okay? We only needed to go out to 3 terms. And this guarantees it, right? Okay, let's go out further. Plus 0.00002 minus, okay, we don't need to go any further. So just to clarify what we did here. So this term is this term. 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 Okay, at this point, we are now 4 places after the decimal accurate. So all we need to do is add these 4 values together, and that gives us what we wanted. So, oops. Now we say is approximately equal to negative 0.0847 accurate to 4 places after the decimal. So if we were rounding to that specified threshold, right, 4 places after the decimal, this is that exact value in that representation. Of course, it's all approximation. We're never actually going to get to the value unless we know the exact transcendental number that it happens to be equal to. We usually don't, though. And so that's the power of the alternating series estimation theorem. And it all comes from this very helpful visual tool that says alternating series are going to bounce back and forth between the, so every successive partial sum gets you closer to the limit of that series and no further away from that limit.